Hear me well? Oh, great. So hello, everyone. I'm John. I'm a PhD student in the software research group at ETH Zurich. And today I'll present our work, Rawsamble, overlapping and assembling raw nanopore signals using a hash-based seeding mechanism. So let me start with an executive summary. There are many recent works that aim to map raw nanopore signals to reference genomes without base calling them. We already also covered some of these works yesterday as well. But we also find that these existing solutions cannot really interpret or analyze these raw nanopore signals directly if a reference genome is unknown or does not exist. And our goal in this work is to enable raw signal analysis without a reference genome. So we make three key contributions. First, we propose Rawsamble, which is the first mechanism that can find all versus all overlapping between raw nanopore signal pairs without base calling them. We also built the first de novo assembly directly from raw nanopore signals, again, without base calling. And also we implement a new assembler that can essentially build and output the assemblies of raw nanopore signals. Across three genomes of varying sizes, we show that Rawsamble provides a fast throughput of from 140x to 1000x faster with a single CPU thread than the throughput of a single nanopore. And we also, when we look at the overlap statistics, we find that 37% of the overlapping pairs that Rawsamble finds is also shared with Minimap2 overlaps. And when we construct the de novo assembly from these raw signal overlaps, we find that we can construct unitics of length up to 1 million nucleotides from overlapping raw signals, again, without base calling. So let me cover some background. So nanopore sequencing is a widely used sequencing technology, as we also seen in many talks today and yesterday. It can sequence ultra-long essential fragments of nucleic acid molecules up to 4 million bases. It offers high throughput, it is relatively cost-effective, and it also enables these unique features such as real-time analysis and portable genome analysis. So let's see how nanopore sequencing works. So here you see a nucleic acid molecule getting sequenced as it moves through this tiny pore called nanopore. And as this molecule moves through that pore, the ionic current measurements or raw electrical signals are generated in real time at certain throughput. And as these signals are generated, we can even start analyzing these electrical signals during the sequencing time, which we refer to as real-time analysis. And even further, we can utilize these real-time analysis to make some real-time decisions. For example, to stop sequencing of a read early if further sequencing of that read is unnecessary. So there are usually two ways of analyzing these raw nanopore signals. One traditional way is to translate or base call these signals to bases before the analysis, which can then be followed by the regular analysis steps such as read mapping with Minimap2. And this type of analysis is usually accurate as they are less noisy than using raw electrical signals. And we know that there are many tools, of course, available that can use these base call sequences. But when you use these, actually, these are usually the computation requirements usually tend to be costly and power hungry, especially if you are using the base calling, if you are running the base calling step with powerful GPUs. And there are also these recent works that can directly analyze or map these raw signals to reference genomes without base calling. And they tend to be usually more efficient, provide more efficient analysis with better scalability and portability. And we also know that raw signals retain more information than just individual bases. For example, we can infer the methylation from the signals. But we also see that there is a lack of established tools for further downstream analysis when using these raw signals. So let's see how essentially we can map the raw signal to a reference genome using the state-of-the-art mechanism. So it usually starts with converting the reference genome into its electrical signal representation that we refer to as synthetic signal using a conversion table that essentially takes each chimer in the reference genome and converts it to its expected electrical signal so that we create this synthetic signal from the reference genome. Then we somehow generate hash values from both this synthetic signal and the actual raw signal so that we can essentially perform this regular hash-based seeding and mapping steps to do the mapping. So the use of synthetic signals usually provide more noise-free analysis, let's say. But essentially to perform this analysis, the reference genome must exist so that we can do the mapping. So we find that the existing solutions cannot analyze raw signals directly without the reference genome. And if you really want to go beyond reference mapping, what you could do essentially overlapping, for example, to build the de novo assembly. And to do this, we could simply essentially replace this hash value generation from synthetic signal maybe to the use of raw signal, but essentially there are three main challenges to it. First, now instead of essentially dealing with one noisy signal, we're dealing with the two noisy signals. Remember, synthetic signal was essentially relatively noise-free. Now, and also, instead of now finding the best mapping per read, we need to find all overlapping pairs for all versus all overlapping. And also, we need to generate long paths from many overlaps to build long de novo assemblies. So let me cover the Rawsamble mechanism then. So our goal is to enable raw signal analysis without the reference genome. To this end, we propose Rawsamble. Rawsamble is the first mechanism that can quickly and accurately find all versus all overlapping of raw signals without base calling. We built the first de novo assembly directly from raw signals, again without base calling, and also we implemented new assemblers to build and output the assemblies from signals. Rawsamble has two high-level basic key ideas. We build on the existing state-of-the-art raw signal mapper, raw hash, and we extend on this to support the overlapping. To explain the changes that we make in with Rawsamble, I'll first quickly explain you how raw hash works in a very high level. So as it so happens with any read mapper, it has two steps, indexing and mapping. And in both steps, the reference genome and the raw electrical signal is converted to a set of, let's say, discrete electrical signals to discrete values that are known as event values. And then to remove some noise from these signals, the quantization is applied, and then the hash values are generated from these quantized signal values so that we can find matching regions between the reference genome and this raw electrical signal so that we can then follow the usual chaining and mapping steps to find the best mapping position for a read. So we make three key changes in this pipeline. First, we make some changes in the indexing step, and also we make changes in the chaining, and also some changes in the outputting strategy in Rawsamble. So now, instead of essentially constructing in the index the hash table from the base call sequences, the synthetic signal, we essentially directly use raw electrical signal to construct the index. So this means that we're essentially free from the conversion table that is used to construct the synthetic signal, right? But now, essentially, we're including, let's say, more noisy electrical signal in the hash table. And we somehow want to basically get rid of, somehow eliminate most of this noise from the electrical signal that we're storing in the index. And we do this by performing some aggressive filtering in the signal so that we can avoid some nanopore-specific, nanopore-related errors better. So to also illustrate this, it may so happen that we may, let's say, generate these discrete set of signals, and some of these adjacent signals can be very close to each other. So this can actually, this can mean that we may have some skip and stay errors there due to this conversion mechanism that we're applying. And what we simply do is that we filter most of these signals if they are close to each other by just keeping only one of those. So we also make some changes in the chaining and the outputting strategy. For chaining, we adjust the minimum chaining score to avoid false chains. This is because the all versus all overlapping tends to find a larger number of seed-hits than mapping the read to a reference genome. So we simply adjust the minimum chaining score during overlapping that we set to be a 5x larger value than basically the chaining score we use when mapping the read to reference genome. So we also make two changes in the outputting strategy so that we can construct de novo assemblies better. So instead of reporting the best mapping per read, now we report all chains so that we can enable a raw signal overlapping with many other signals so that we can do all versus all overlapping. And then we also avoid the cyclic overlaps, potential cyclic overlaps, with some simple comparisons between read names as also used in the Minimap 2. So to illustrate this, imagine we have these two raw signals that are overlapping in this particular region. So if when we're processing the first signal, we're going to find these overlaps. But then when we're processing the second signal, this means that we are also going to find these overlapping regions between these two reads. But if you report these two overlaps, then this means that we're creating some cycling information in the overlap output that we could provide. And we simply don't report the second overlap information by simply looking at the read names so that we avoid the cyclic overlaps. So then with that, I'll go over the results. So we compare the Rawsamble overlaps with the overlaps that the Minimap 2 finds on the forward strand. So Rawsamble is also integrated within Rawhash2. We also assess the, let's say, quality of the overlaps that we're generating by constructing de novo assemblies from these overlaps using Miniasm. And also we discuss some more directions in the later slides. We have 3 evaluation metrics. First, we evaluate the speed, the performance in terms of throughput, which is basis process per second per CPU thread, and also the overall time. We also measure the percentage of shared and also unique overlapping pairs between Minimap2 and Rawsamble. And we also construct de novo assembly and look at some assembly statistics. We use 3 data sets, E. coli, yeast, and a human genome, across different sequencing depth of coverage, including 500x coverage for E. coli and a half an X coverage for human. So we first look at the performance and the peak memory usage. Here we have these 3 different data sets, and then we compare Rawsamble and Minimap2, and we show the overall execution time and also peak memory usage. So first thing we see, Minimap2 is substantially faster than Rawsamble, but it's good to remember that Rawsamble avoids the base calling step. So in order to use Minimap2, you should first run the base calling step. Also, Rawsamble is designed to be used for real-time purposes. So for that, it also outputs the throughput information. So if you want to do real-time analysis, then it means that you need to do the analysis. You need to provide a faster throughput than the throughput of a sequencer. And the throughput of a single nanopore, again, to remember, is around 450 bases per second, which is the data generation speed. And a single sequencer usually has 512 nanopores. We see that Rawsamble provides from 140x to 1000x faster throughput with a single CPU thread compared to the throughput of a single pore. This means that using either a single CPU thread or a few threads, you can essentially do real-time analysis of the entire sequencer. So we also look at the all versus all overlapping statistics in terms of the percentage of overlapping pairs here, as shown in this Venn diagram, in terms of to show the shared overlaps between Rawsamble and Minimap2, and also the unique overlaps, the overlaps that are unique to either Rawsamble again or Minimap2. So we find that on average, 37% of overlapping pairs that Rawsamble provides is also shared with Minimap2. But the question is essentially, so how can we evaluate the impact of these ratios, right? So to evaluate this, we build a de novo assembly from these overlaps. And remember, also our goal is to be able to build long de novo assemblies directly from raw signals. Since both Rawsamble and Minimap2 provides the overlapping information in path, we can directly use Miniasm off the shelf to generate the assembly graph. So when we do this, we generate the assembly graphs, again, from these data sets using Rawsamble and Minimap2 overlaps, and then we show these assembly statistics here in terms of M50 length, average unitic length, maximum unitic length, and also the number of unitics. But really the key takeaway here is that what we see here essentially, now raw signal overlaps can be used to construct de novo assemblies without base calling. So this is, in my opinion, the biggest key takeaway here. But again, if you look more closely to the statistics, what we see here, again, overlaps from Minimap2 lead to longer unitics. But this is expected because the Minimap2 uses less noisy sequencing data, which is the base called sequences. So then this means that we need maybe perhaps more accurate a raw signal mapper tool so that we can generate more accurate overlap information. We also visualize the assembly graphs that we're generating with Bandage. So this is the assembly graph from Minimap2 on the yeast genome. And this is also the same genome Rawsamble graph. So to give you the scale, these are the longest unitics in both assembly graphs. So here what we see is that we can construct the unitics essentially can be assembled into long components using essentially raw signals. And perhaps we can even construct components that are perhaps even less complex than the context that the Minimap2 overlaps are leading to. So we enable 3 key new directions, perhaps more, in raw signal analysis. First, we can construct and analyze de novo assemblies directly from raw signals. So this is what we evaluate and show in this work. Also, second, maybe we could utilize the overlap information for more accurate base calling. So remember, we use these raw signals to do the base calling. But what we could also further do, we could generate the overlap information between signals and perhaps input this also overlap information to base caller so that maybe we can improve the accuracy of the base calling. Third, we could also utilize the constructed assembly again for base calling, perhaps. From overlaps, we know that we can construct assemblies. Maybe even we could do some error correction on this assembly. And then instead of using each of these raw signals, we could simply base call this the raw signal assembly, and then this would avoid base calling each of these raw signals one by one, which could be useful for performance and perhaps accuracy reasons. So the source code of Rawsamble is available here in this QR code. You can access it, which is integrated in Rawhash 2. And the preprint is going to be available soon. So this is, in my opinion, a very nice collaboration effort between two groups, mainly two groups at ETH Zurich. We also have this Rawsamble, which is a raw signal assembler, which is in the beta version now. This is the slightly modified version of Miniasm that outputs the assembled raw signals instead of base code sequences. It supports all major raw signal file formats from FAST5, POT5, and SLOP5. This is still in the testing phase, so feedback is appreciated. To conclude, we make three key contributions. We proposed the first mechanism that can find all versus all overlapping. We built the first de novo assembly from raw signals without base calling. And then we implement a new assembler to build and output the assemblies of signals. We show that Rawsamble provides a fast throughput compared to throughput of a single pore. When we're looking at the overlapping statistics, it shares a large portion of overlaps with Minimap2, and then we can also construct very long unitics of the million nucleotides. We believe that there are many opportunities exist for analyzing raw nanopore signals. Indexing is very cheap, at least in terms of performance, and we believe that, and actually I showed these 2 points also last year at ISMB when presenting Rawhash, which I'm going to repeat it again. So we believe that maybe many future use cases exist for on-the-fly index construction. And we should also rethink the algorithms to perform fully downstream analysis, fully using raw signals. And I'll add this year one more point here. Maybe we should rethink the base calling approaches, again, to integrate the information from raw signal analysis. So with that, I'll conclude my talk and happy to take questions.
Thank you. So we have a couple of questions over there.
That was really interesting. I guess one thing, a point of clarification, the config for human, the N50 that you showed, was that kilobases or megabases?
It's kilobases because we use a half an X coverage. The coverage is not very high.
25, is that right? 25 kilobases?
Should be. Let me go back very quickly.
23 point, is that right?
That is correct, yes.
That seems awfully small to me.
That's correct.
What was the average read length that went into this?
Of the reads.
Yeah.
So the mean length is around 8 to 10K of the reads. So we believe this is mainly because we have also too many short unitics, which is essentially keeping the N50 down over there. But I think this result is particularly interesting because Minimap2 even provides even smaller N50 unitic over there.
I mean, I strongly suggest getting better data because that input is too small, and it's not the advantage of ONT. ONT can generate very long, but one obvious application is neonates in intensive care, right? If you can, and there are actually samples now. What I would encourage you to think about is actually comparing, making a hash, I guess, comparison between a mother, father, and child. Because what people are trying to find is the de novo events very fast. And there's a big field on this right now with the long reads. And if you could do it without base calling, in principle, you would save time, which will get a report to the NICU much faster. So if you're interested in that, I can hook you up with people that are doing these experiments right now. But I think you'd have to extend two things. You'd have to get much larger contigs for sure. But then you'd also have to be able to compare 3 people simultaneously, mother, father, and child. And then what I would suggest you do is local assembly for the potential de novo units, because if that could be shortened, you might actually save lives, which would be fantastic.
Extremely useful suggestions. Thanks a lot, Evan, definitely.
Okay, another question.
Thanks for the interesting work. So like the shared ratio of the identified overlapping pairs between your method and Minimap2 is I think it's very low. Why is that?
Well, so So good question. I think this is mainly because of the parameters we're selecting. So we might be simply reporting perhaps too many also overlaps that are not, that the Minimap 2 is not finding. What we don't know if these additional overlaps is simply also, let's say, mainly the correct overlaps that should have been found by Minimap 2, but it cannot, and we simply can't find it. So that still is a question that yet to be answered. We are confident that these overlaps, most of these overlaps, although most of them are not shared, these overlaps are creating very useful information because we are able to construct very long unitics that are perhaps still not very comparable, but still long enough, let's say, to believe that these overlaps are mainly useful.
Okay, one very last question.
I was wondering if you were planning on incorporating your method into MinNo, because you can't really do adaptive sequencing unless you incorporate it into MinNo.
So exactly, this is a very good question and suggestion. We have actually currently have these efforts integrating it with MinNo. MinNo has its own disadvantages, which there's this particular delay, even though we stop the sequencing. But still, hopefully very soon, we're going to be able to integrate with MinNo.